Great, let's go ahead and do some study one data analysis. So what you're seeing is my screen. And in the screen we have a console on the left, we have the environment at the top right, and a set of files in the bottom right quadrant. And I've got the project open that's called Study One Data Analysis. And yeah, let's analyze some data. So I'm going to go ahead and open up a new script, a new R script. And that means we have a blank page in which to actually start crafting a script that will analyze our data. So one of the first things that we always need to do is load the libraries that we're going to be using. So I'm going to go ahead and make a comment that says load libraries. And for today's data analysis exercise, we're going to use three different libraries, otherwise known as packages. We're going to use the psych package to produce descriptive statistics. We're going to use a package called fsize, E-F-F-S-I-Z-E, to calculate effect size, Cohen's d effect size. And we're going to use a package called ggstatsplot to produce a plot so that we can actually graph the results. So having written all three of these commands, I'm saying library and then in parentheses the name of the package or library that I want to open, or load, I guess is the other word. And I'm going to go ahead and select all three of these lines, and you can either click run, which I will do now, or you can hit Control Enter on the keyboard. And now all three of those libraries are all set and ready to go. So I can't do anything, of course, until I have some data loaded up. So I'm going to read in the Study One data analysis file. And I'm going to actually enter a parenthetical comment here, which is that we're relying on only 100 randomly selected cases from our larger data file. As you might remember from the first lab last week, I don't know why I said first. Anyway, from lab last week, you analyzed the participant characteristics, and you might recall that we had 395 participants. So I've created a data file that has just 100 of those. So if you look in the Files section of RStudio here, you'll see that I've got two different data files. The one that you all are going to analyze is called study1_data_for_analysis.csv. What I'm going to open right now, though, is this one that also adds _n100 to signal that it's the file that represents just 100 randomly selected cases from our larger data set. So I want to create an object as usual. I tend to call it data. You can call it whatever you want. Using this backward pointing arrow so that R knows what to put in that data object, and what it should put in that data object is the CSV file that is our data file. So we'll use the read.csv command as we have done before and tell it where to find this file. Well, the file is located, of course, in the files folder that I pointed out before here in the bottom right quadrant. And it's located right next to the script that we're actually using. So all we need to do is indicate the name of that file, which is Study One Data for Analysis _n100.csv. For me, you again are not going to have _n100 in your file name. You're going to just use the one that has all 395 cases. Okay, so having created that command, I can run it, and I'm going to hit Control Enter on my keyboard. Because the cursor is on that line, it will run the command on that line. And yeah, you can see that in the environment, I now have an object called data. And if I open up that object, we can inspect it. We can see what we got there. We have a variable called condition_label, which you can see reflects whether or not people were in the static or the dynamic condition by random assignment. We have a variable called interest meet. That is our primary dependent variable of interest. It's the interest in reducing meat consumption, which range from 1 to 7. That was the possible range of values. We also have other dependent variables, the number of meatless meals they think that people who are trying to reduce their meat consumption eat per week. We have percent limit meat, which is what percentage of people do they think are trying to limit their meat consumption. And then finally we have two variables that reflect participant characteristics that Sparkman and Walton asked their participants to provide. Political orientation, this is the variable called ideology that you worked with when you were determining participant characteristics, and gender underscore coded, which was coded into one of three categories based on people's open-ended responses. People were coded as identifying as male/man, female/woman, or I'm scrolling to see whether we have any of the third category represented here. Yep, third category non-binary. And I believe there was a fourth category of declined/other. I don't think we have any of those represented here, so that's fine. These are the variables, 1, 2, 3, 4, 5, 6 variables that you'll see reflected in the Study 1 Data for Analysis CSV. This one has some extra columns that you don't need to worry about. Those are columns that got created because I was trying to randomly select 100 cases from the 395 that we actually are going to use for analysis. So I think that does it for describing the file. So I'm going to go ahead and close that up so that we can go back to our script. And the first thing that's always a good idea to do is to look at your data. Always look at your data. So let's see, how is the best way to look at the data? Well, why don't we go ahead and generate a frequency distribution. And again, I'm writing a comment every time above the commands I'm running so that it's clear to anybody looking at this script what I'm doing at every stage along the way. I'm not just doing this to you. I do this in all of my scripts. It's good coding practice to comment so that people can read what you're doing. It's actually not just helpful for other people. I have written scripts where I'm very glad that I wrote comments because it made it much easier to figure out what I was doing and why. So, okay, we're going to generate a frequency distribution showing interest in reducing meat consumption, our primary dependent variable. We're going to want to see what does the variability in interest look like in our sample. So we'll use the hist command. That's a function that's part of the graphics part of base R. It comes with R naturally. And we're going to say we want to look at the interest variable, which is in the data object. So we'll do data, $, and then tell it which of those variables we want to look at. Well, it's interest meat. So I can just, it popped up automatically. I can select it and it will autocomplete for me. And now I will hit Control Enter so that we will generate the frequency distribution and it will appear in the bottom right of my window. Excellent. So I'm going to go ahead and zoom in so we can see this a little bit better. Whoa, that's too much zoomed in, isn't it? I wasn't expecting that. Okay, let's zoom. Let's not zoom. Let's see. Can we make it smaller? All right, forget that. We'll just look at it right here. Sorry about that. I don't know what happened there. Okay, so we have values ranging from 1 to 7 for interest on the x-axis. Those are the possible range of values for interest in reducing meat consumption. On the y-axis, we have the number of people who selected each of those 7 values. And you can see that the modal value here is that's interesting. I wonder if it's 3 or 4. I can't tell based on the way these bins are set. But it's somewhere in the middle between 1 and 7, as you can see. And then the values get less frequent as you move out to the extremes, values of 1 and 7. And in terms of the distribution, it looks normally distributed, or at least approximating normal distribution. So nothing here that is raising big alarm bells. It doesn't look to me like we have huge outliers. I think we can actually proceed to do the main event, which is, oh no, I'm sorry, it's not the main event yet. First, before the main event, let's summarize this variable a little bit. Let's get some descriptive statistics so that we can describe what in the sample as a whole is the level of interest in reducing meat consumption. And we can use the psych package to get those descriptive statistics. For interest, I'm just going to say for interest, we know that it's for interest in reducing meat consumption across the whole sample. This is what's called a grand mean. It's the mean interest plus its standard deviation across everybody in the entire sample. And we can use the function from the psych package that is called describe, appropriately enough, given that we're getting descriptive statistics. And we want to tell it that we're interested in the variable that's in the data object called interest meet, which again pops up. Once I hit data $, it shows me what are the options, so I'll go ahead and hit enter to say, yes, I'm interested in describing the variable called interest meet. Okay, so I've got my cursor on that line. I can hit Control Enter. And when I do that, I can see in the console what the mean and the standard deviation are for my 100 cases. So we have a mean interest across everybody in the sample of 4.06 with a standard deviation of 1.58 for those n equals 100 people. So those are the three values that are most pertinent to what we're thinking about right now. We can also see that the median here is 4, which means that 50% of the people in this subset of 100 subjects have a value of, 50% have a value above 4 and 50% have a value below 4. That's what that means. Okay, great. So let's get a little bit closer now to figuring out whether or not interest in reducing meat consumption varies as a function of whether or not people read the dynamic descriptive norm information or the static descriptive norm information. And to do that, we're going to again use a command out of the psych package, but it's going to be the describe by command. So I think for shorthand, I'm going to go ahead and copy this comment above here because we are interested in getting descriptive statistics for interest, but instead of across the whole sample, we're going to get it for each norm condition. And once we do that, we can enter the actual command, and we're going to use describe by. And again, it's the same variable. So I can go ahead and move the mouse, select that here, copy it, and paste it within the parentheses so that it knows now in the describe by command that we want to describe interest in reducing meat consumption, which is part of this data object. But we need to tell it a little bit more information. So I'm going to enter a comma here, and I'm going to hit return just to kind of keep this looking neat. And I'm going to tell it what is our grouping variable. Well, we're going to say group equals, and then tell it it's a grouping variable that's located in the same data object. So we'll say data $. And in this case, what we're going to use is condition underscore label. Remember, that's the variable that indicates whether people were in the dynamic or the static condition. And that's the full describe by command. So now it's going to give us the same information that it did across the whole sample separately for people in the dynamic condition and people in the static condition. So with my cursor on that row, I can go ahead and hit Control Enter to run the command. And there we go. Within the console, we have descriptive statistics by group. We've got group dynamic here at the top, group static in the bottom. And you can see that we have 47 people in the dynamic condition with a mean of 4.02, standard deviation of 1.55. And below that, we have 53 people in the static condition with a mean interest of 4.09 and a standard deviation of 1.61. Again, this is just the 100 cases that we're considering for this demonstration of how to analyze our Study 1 data. So you might be looking at those numbers and thinking, that does not look very promising with respect to the hypothesis. And I would have to concur with that assessment. It looks like these means are really pretty close together. For dynamic versus static norms, it doesn't look at this point like there's much of a difference in the level of interest in reducing meat consumption. And in fact, if anything, the means go in the opposite direction because here we have a static mean of 4.09, which is higher than the dynamic mean of 4.02. Okay, so that's the descriptive side of the coin, and next we will move to the inferential side of the coin. Okay, so to do inferential statistics, what does that mean? Well, in this case, because we have two different between subjects conditions, we randomly assign people to either be in the dynamic or static norm condition, it is appropriate to run a t-test. which is in fact the same statistic that the original authors ran. So we're going to compute a t-test for independent samples, and that's the appropriate test when you have a between subjects manipulation like we do. And to run that t-test, we're going to use the t-test command. So we just type t.test and then open parentheses, and we have to specify a few different things. So first of all, we need to tell it what is our dependent variable. In this case, we don't actually need to tell it which object, because the t-test command has a separate subcommand in which you specify the data file. So in this case, we're going to specify the dependent variable simply by typing interest meet. That's the name of the dependent variable. And we need to say, what is that going to be a condition of? What do we think is going to push interest in reducing meat consumption around? And that thing is condition. So for the t-test command, what we're going to do is use a formula. This is pretty common across different packages in R, is to use a formula to specify the dependent variable, which we're going to look at as a function of, using the tilde, the independent variable, which in our case is called condition underscore label. Okay, so I'm going to have a comma here. Now that we've given the formula, now we need to tell it what data file we're going to use. So we'll say data equals, well, data, because that's in fact what the data object is called. If we had called the data object something else, this would say data equals something else. Okay, another comma, because we have a couple more things to specify. One is we want to specify a student's t-test. By default, R runs a t-test that isn't a student's t-test. It runs what's called a Welch's t-test. Now, actually, I think a Welch's t-test is a great default. It's the one that we should typically run. But what we're doing here is we're going to run the student's t-test, because that is the type of t-test that Sparkman and Walton in 2017 ran for experiment 1. And what a student's t-test is it's an analysis in which it assumes that the variance in interest is equal in the two groups. So we need to tell this t-test command to say that var.equal equals true, which tells it the information it needs to know, you want a student's t-test, because you're going to assume that the variances are equal in the dynamic and the static conditions when it comes to how much variability there is around the mean for interest in reducing meat consumption. Okay, the last thing we need to specify, and actually we don't have to specify it because by default R will do this automatically, but I want us to be deliberate about specifying that this is a two-sided or two-tailed test of the hypothesis. So the last option we want to set is to say, how are we going to test the alternative hypothesis? Well, the alternative equals, and then in quotes, two-sided. And this tells it we want a two-sided t-test. And if we were going to observe an alpha that was different from 0.05, we could specify that. But alpha is 0.05 by default, so we are not going to specify that. We could, but we don't need to. And so we're not going to, just for the sake of simplicity. So this command, all told, will run a two-sided or two-tailed t-test, testing the hypothesis that condition would create variability in the dependent variable interest in reducing meat consumption, both of which are variables that are found in the data object. We're running a two-sided t-test that is a student's t-test, which we're specifying by saying that var.equal equals true. Okay, and that's it. I'm going to put my cursor here on the last line and run this command by hitting Control Enter. And by doing that, we can see the result of the t-test in the console. We have a two-sample t-test. It's telling us that we were using the data object, and we're testing for the formula interest by condition label. Here is the t-value. It is minus 0.23 with 98 degrees of freedom. Again, remember, we're actually doing this demo video on the basis of only 100 cases. The degrees of freedom for a t-test is n minus 2, which is why the degrees of freedom here is 98. And the p-value is 0.8183. And you know from having thought about t-values and p-values before that what this means is that the probability of having a t-value of minus 0.23 or plus 0.23 is 81.8% if the null hypothesis were true. So, in other words, it's not that unlikely that we would see a difference in the means for the dynamic and the static conditions that results in a t-value of only absolute value 0.23. In this case, it's minus, but of course it could have been positive 0.23. We were doing a two-tailed test. The probability of having a t of that size, which is pretty small, is pretty high if the null hypothesis were true. And that means on the basis of these 100 subjects that we are not going to reject the null hypothesis, that dynamic norms would reduce interest in, the dynamic norms would increase interest in reducing meat consumption compared to static norms. That hypothesis does not have support on the basis of these t-test results with this 100 subjects that we've looked at. And so the last thing we're going to do, even though we don't actually have a significant effect, we're going to go ahead and finish this out by computing an effect size. And a useful effect size when you have two different conditions that you've randomized people to experience one of is the Cohen's d. So let's go ahead and compute Cohen's d effect size. And as I mentioned earlier, we're going to use the F size, EFF, SIZE package to compute Cohen's d. And the formula is actually not too confusing. So we're going to go ahead and say, let's use the Cohen.d command from the F size package so that we can compute Cohen's d. And then we're going to open our parentheses. And this is a command where we actually need to tell it what's the data object that we're going to use. And it's called data, again, as it has been from the very beginning here. Data, $, to say we want to specify a variable within that data object. And then we're going to go with interest meat. So that is our dependent variable. And now we need to tell this Cohen.d function or command what is going to be the independent variable here, the factor that should have an effect on interest meat. And that factor is, after entering the comma here, F for factor equals data object, $, to indicate the object we're working with and that we want a variable within that object. And of course, you can see the options popping up, and we're going to go ahead and go with that first option, which is condition underscore label. That is the factor of interest here. And that's actually all we need to specify so that we can run this Cohen.d command. So I'm going to hit Control Enter on my keyboard to produce Cohen's d, which you can see is in the output here. So it's telling us Cohen's d, the estimate itself is minus 0.046 or minus 0.05 if we round to 2 digits. It's also handily giving us a description of that. How would we qualify the size of that effect using the language that you've heard before, negligible, small, medium, or large? Actually, negligible is probably new to you. We've talked about small, medium, and large, but not negligible. In this case, this Cohen's d is so small that we're saying that its size is negligible. In other words, it's kind of near zero. We're also getting the 95% confidence interval for that Cohen's d estimate. So that ranges from minus 0.44 all the way up to 0.35, which means that on the basis of the values that we have from this sample, there's quite a bit of uncertainty about what the actual effect size is in the population. It could be small to medium in the negative direction, minus 0.44, or it could be actually small-ish to medium, sort of in between there, in the opposite direction, the positive direction. how do we figure out what the direction is in this case? Well, here is where actually appealing to the means will help you understand how the software is actually calculating whether or not the value for the effect size for Cohen's d in this case and the t value here is negative or positive. Okay, so I'm again looking at the console. I'm looking now at the results for the t-test. You can see that the mean for the dynamic condition is 4.02 on the basis of our 100 subjects. The mean for the static norm condition is 4.09. Based on those means, I know where this negative t-value is coming from. It's calculating this t-value, and the same is true for Cohen's d effect size, by subtracting the static condition from the dynamic condition. And when I do 4.02 minus 4.09, I come up with a negative value. So that's why the t here is negative. If, in fact, it had computed the t-value in the opposite direction, so that in the numerator of the t-test, it was going to be static minus dynamic, then that t-value would have been the exact same size, but it would have had a positive sign to signal that the static mean was larger than the dynamic mean. But again, because it was computed in this direction where it's dynamic minus static, we have a negative t-value and in parallel this negative Cohen's d. Okay, let's see. I think that's it as far as the t-test results and the effect size. We have one more thing to do, which is this is all fine, but really you should always look at your data. So let's finish this out by graphing our results. So I'm going back to the script. I'm going to create a comment saying, hey, let's graph the results. And we're going to use a command out of the ggstatsplot plot package called ggBetweenStats. So I'm going to type ggBetweenStats. Ah, look, R is smart because we loaded the ggstatsplot plot library. We started typing letters that match a command in that package, and I can just go ahead and hit enter, and it'll be all set for us to tell us what are the options we want to specify for this ggBetweenStats command. So I am going to specify a number of things, so bear with me. First of all, I need to tell it, well, what data am I going to use? And you're not going to be surprised to know that the data we're going to use is called data. So it's data equals data. Okay, great. The next thing that ggBetweenStats wants to know is what is the factor or the predictor, or otherwise known as the x variable. It's the variable that we would plot on the x-axis. And we're going to say x equals condition underscore label. Great. Now, ggBetweenStats lets you actually set labels for the x-axis variable as well as the y-axis variable. So let's go ahead and set the x-axis variable right now. And for that, we'll use the command, or subcommand, I guess I should say, the argument called xlab, xlab, which says what's going to be the label for the x-axis. So we say xlab equals, and then I'm just going to call it condition, which is, I believe, close to what Sparkman and Walton might have called that x-axis. In fact, it might be exactly the same. Actually, I can't remember, but it's a good descriptor that tells anybody reading your paper that we're looking at the effect of condition, which is the variable that we manipulated. Okay, great. So now I'm going to enter a comma here, hit return, and now let's specify the dependent variable. And the dependent variable is the variable that goes on the y-axis. So it's y equals interest meet, which is the name of that dependent variable. Then we're going to have a comma, and we're going to do the same thing we did for x. We're going to give a label for the y-axis, which is ylab equals, and here I'm going to call it self-reported interest, just like Sparkman and Walton did, in quotes, because that's a string. And then I'm going to hit a comma because we have still yet some more things to specify. Okay, comma. Now, this is a little hard to explain, but I'm going to try my best. The next thing we're going to do is, see, GG between stats is going to give us a bunch of information in this graph, not just a figure. It's also going to give us the t-test results, the effect size results, the confidence intervals around the effect size, the sample size. It's going to give us a lot of information. So for the task it's going to do in terms of giving us the effect size, we need to tell it what type of effect size to give us. So the subcommand here is fsize, EFF, dot type, because we're telling it what effect size type to do. I'm going to say that equals, now you might be thinking we would just say D here. That would be sensible, but that's not one of the options that GG between stats wants to hear. Instead, GG between stats wants us to say, give us the biased effect size. And that's because actually Cohen's D is known to be biased, and many people instead report a different effect size called Hedges G, which is Cohen's D, but correcting for bias based on the size of the sample. Because Sparkman and Walton reported Cohen's D, that's what we're going to report too, and that's why we're asking GG between stats to give us a biased effect size type, which means it's going to give us Cohen's D. So after putting biased in quotes after the EFF dot type equals subcommand, I'm going to hit a comma. And let's see, we are going to also tell it that we want the plot type of a box, so that it will give us the box plot around the mean. So I'll type plot.type equals, and in quotes, box, end quote, comma, excuse me. Wow, this goes on and on, doesn't it? The other thing we want to tell it is, yes, give us the means, plot the means for us in these big red circles so that we can see what the mean is in each of the two groups. So to tell it that we want it to plot the mean, we can type mean.plotting equals true. In other words, yes, please give us the mean, plot that mean. And then after saying equals true, we give a comma. And just like we did for the t-test, where we told it we want a student's t-test, where we're making the assumption that the variances are equal, we're going to tell GG between stats the same thing. We want that t-test to assume equal variances. So we type var.equal equals true. And then the last thing we're going to do is, you don't have to do this, but we're going to tell GG between stats to apply a theme. And that theme will give us a plot that is in APA style, basically. It's a plot that doesn't include grid lines, either horizontally or vertically. And it's the kind of plot that would pass muster at an APA journal. And because you're writing an APA style empirical report, it makes sense that we're going to apply that theme. And to apply that, we're going to say GG theme equals, and here we're going to use, I know this is a little bit confusing, but we're going to use we're using another package within this package. So within the GG stats plot package, in which we're using the GG between stats command, we're going to use another package called ggplot2, which has a theme embedded in it that we're going to use called theme_classic. So we need to tell GG between stats, hey, we're going to apply a ggplot theme here. So GG theme equals ggplot2 : and then tell it which theme we want. You can see that there's a lot of different themes that we could apply. We're going to apply theme_classic. And that's it. That finishes the command. I know that was a lot of rows and a lot of sort of specific details, but having done that, we're going to get a kind of cool looking plot. And it'll look familiar because I've shown you a plot very much like this in lecture, but not with these data, of course. So let's look at this plot. I'm going to go ahead and plot it. We already know what the means are because we got those when we ran the t-test and we ran descriptive statistics. Now we're going to plot those means as well as all the data in a pretty cool, transparent way. All right, so now here we have that plot, and the plot shows up in the plots window at the right. And you can see we have a lot of information here. I am going to just call out a couple of things that will help you interpret what we see. On the x-axis, we have condition. We have the dynamic folks on the left, the static folks on the right. There are 47 people in the dynamic condition, 53 in static. We have the mean in each of those two groups, signaled by this red dot here. On the left, the mean for the dynamic group is 4.02, and on the right, the mean for the static group is 4.09. We also have dots, which reflect all the individual observations. That's the level of interest for every participant in the sample. On the left for the dynamic group, those dots are in green, and on the right in the static group, those dots are in orange. And so you can see there's variability around the mean in each of the two groups. You can also see that those means, at least in this subset of 100 participants, are really close together, which we knew because we already had the means from before. We had the standard deviations too. We also knew from the t-test that the difference between those two means was not statistically significant, and it's not surprising. And so now we can sort of visualize all of that here in one graph. Notice that the ggBetweenStats command also gives us the t-test results for the student's t-test that we computed. It gives us the Cohen's d value along with the 95% confidence interval around this value of minus 0.05 in this subset of 100 people. It also gives you some information about Bayes factors, which we're not going to address yet at this point in the semester. That's actually something that we will return to later in the semester, assuming everything goes according to plan. So we're going to sort of skip going over that or thinking about that for the moment. For the moment, the main issue here is that we have this graph of the results that you can actually copy and paste into your own Word document in which you're summarizing the results of the Study 1 analyses. Now to do that, all you have to do is in this plots window, click on the export button there. What I'm going to do is copy to clipboard, and it opens up a bigger window. And all I have to do in order to save this plot to the clipboard is to right click on it, which I'm doing with my Windows mouse, right clicking. If you're on a Mac, you can hit both. Just use two fingers on your mouse, and that will operate like a right click. I'm going to copy the image, and then I can paste it into any location that I want in a local document. I don't actually have a local document open, so I'm not going to follow through and paste the figure that I just copied to the clipboard, but when you do that, you will be able to paste it right into your document. When you do so, paste it so that it is an image or a picture, and it will show up just fine in your Word doc. So I can close this now and say, look, we are well and truly done with everything that you need to report in your empirical report for Study 1. Now, you're thinking probably, of course, that the authors actually reported more than what we've done so far. And you're right. And if you're curious, you can certainly go on and run some of the extra analyses. But all we really want to see in your empirical report for Study 1 are the values that we've just computed here up to this point in the video.